Hello, my name is Lukas Graf, and in this talk, I want to present to you our paper Site-Constrained Dynamic Traffic Equilibria, which is joint work with Tobias Harks. In this paper, we are looking at dynamic traffic assignment problems, that is, models for car traffic in road networks. And specifically, we are taking a game-theoretic view of these models. That is, we are looking at equilibria in these models, where all the individual drivers act selfishly, choose their path through the network in a selfish way. And then the new contribution of our paper is that we want to add site constraint to this dynamic model. So think, for example, of a road network which has a bridge at a certain edge, and this bridge, for safety reasons, has some limit on the total number of cars that are allowed on this bridge at the same time at any point in time. Now, to get us started, I want to recall first a model you probably are already familiar with, namely the static model, the same situation. So we have a road network modeled here as a directed graph. And then we have a certain number of commodities, each commodity representing a certain volume of flow, so a certain number of cars. But cars are here considered as infinitesimally small flow particles. So the traffic flow itself will be a continuous flow. And so every commodity has a certain fixed volume of flow and some start node, some destination node. And so there are a certain set of paths available to every commodity. And then every particle from the commodity chooses one of these paths. And the collection of all these route choices can then be represented by a vector xp that for every path p has the volume of flow entering this path. And then given such a flow, represented by such a vector, we can compute the cost of this flow on every path, typically something like the travel time of each path, by some path cost function that typically just takes the load on each edge and gives us the travel cost of this edge. And within this model, we can now define an equilibrium in the natural way, which gives us the famous wardrobe equilibrium. Namely, we have some path inflow vector, and this is a wardrobe equilibrium if whenever there's positive inflow into some path, xp, then this path must be a cheapest or shortest one among all the paths available to this commodity. Now, within the static model, we can also add site constraints. Like, for example, on this last edge, there's some limit on the volume of flow that's allowed to take this edge. And this constraint then limits the set of feasible strategy profiles. So we have some subset set of x. Right? And with that, we can again define an equilibrium. And now an equilibrium, a site constraint equilibrium, is, well, a feasible strategy profile from this constraint set. And again, it's a path flow vector in such a way that whenever there's positive inflow into a path, it's a cheapest path, but only among those paths available to that commodity that are still unsaturated, right? So we're only comparing to those paths under the given flow profile where there is still some room left to switch to. And this type of site constraint equilibrium is also well known and has been studied extensively in the literature. And now with this, we want to go back to the dynamic version. So what changes if we go from static to dynamic? Well, basically, we add a time component to this model. And this time component has two effects. One is that now our particles not only can choose a path, but also a starting time, so when they start their journey. And so now the collection of all the route and starting time choices of all the particles can be represented by a vector of functions, right? And these functions give you for every path and every time the rate at which particles entering this path at that time. Right? So we are a vector of path inflow rates. And then the second component that changes is now that also the flow itself through the network changes dynamically with time, right? So particles enter an edge over time, then traverse this edge taking some time. Some congestion effects may take place, modeled here as a queue. And then, of course, the inflow into certain edges may change over time. And so we have some dynamic flow here. And this dynamic flow then leads to dynamic travel costs, right? So the cost of traversing a certain edge changes over time. And this is then captured by what is called an effective path delay operator, which takes some vector of path inflow rates, so our strategy profile, and gives us back a vector of path cost, so which tells you for every time and every path what is the cost of entering this path at that time. And this cost may be just the travel time along the path, but may also include some kind of energy consumption on that path, or some penalty for early or late arrival, or other stuff. And with these components, we can again define in a natural way what it means to be an equilibrium, now a dynamic equilibrium. And it's basically the same thing as in a static case. A dynamic equilibrium is just some path inflow vector, such that at every time where there's positive inflow into some path, then this path must be a cheapest one among all the alternative paths available to this commodity, but also compared to all the alternative possible starting time, the particle starting at that time. And so this gives you the definition of dynamic equilibrium, which again has also been well studied in the literature. And what we now want to do is combine these two ideas of side constraints from the static case and the definition of dynamic equilibria, the dynamic case. And so we again start off with the idea of having some side constraints, right? For example, a limit on the volume of flow at a certain edge, which is now also a function over time, but could also be different things. And at the end of the day, the important point is this limits the set of feasible path inflows, so the set of feasible strategy profiles. And using this, we now want to define a dynamic version of side constraint equilibria. And we can basically write this in a natural way like this. We again limit the set from which we take our flows. And then we also have to compare not to all the alternative paths and times for this commodity, but to some subset of these alternatives. So some set of alternative paths Q and changes in time delta. And so this set UP, called that way because it's kind of the set of unsaturated alternatives. And now already in the static case, there are various different ways of defining what it actually means to be an unsaturated path. And the same is true here. There's not one way of defining that, but different ones. And now here I want to also make this formal. And intuitively, in the case of volume constraints, for example, what we would like to have is that a path and alternative time is unsaturated if a particle is allowed to switch there without violating the volume constraints by switching. The problem with that is that a single particle has infinitesimal size, so a single particle switching will never lead to a violation, right? Because it's infinitesimal in size. And so we can't really check whether an alternative path and starting time is allowed for a particle by trying out this switch, because it would never have any effect on the actual flow. So we introduce an additional concept, namely that of admissible epsilon deviations. So we are now looking at deviations of a whole set of particles, a neighborhood of this single particle which we are actually interested in. And such an admissible epsilon deviations can be viewed as follows. So we are given some flow h, right, which is represented on the left. So we have just two paths and the inflow rates for these two paths. And now an admissible epsilon deviation is a tuple of 4 components, namely an alternative path Q to our current path P, a time frame J, and a rate epsilon, meaning that we are now looking at particles entering path P during the time frame J, and we're taking them at a rate of epsilon. And now these, here marked as red particles, want to switch to path Q, and they want to also change their starting time by amount of delta. Right? And so such an deviation, an epsilon deviation, leads to a new path inflow vector that looks like this. Right? And we will denote by this notation. And now, of course, this is a proper different path inflow vector, so it makes sense to ask whether this is, for example, feasible or whether this violates some constraint. And now with this kind of admissible epsilon deviation, we can go back to what we are actually interested in, namely whether a single particle is allowed to deviate. So to define our set UP. And we do that basically by just taking the limit over these epsilon deviations. So the set just consists of the alternatives Q delta, such that there are arbitrarily small neighborhoods around the current time t, such that these small neighborhoods are allowed to deviate in this sense from path P to path Q and in time from t to t plus delta. And if there are arbitrarily small such neighborhoods, then we say the single particle is also allowed to deviate. And so this completes our definition of side-constrained dynamic equilibria. So we basically need two things to define such an equilibrium concept. We need a constraint set S, and we need a set of admissible epsilon deviations. With these two, we then get a concept of side-constrained dynamic equilibria. And now next we want to make this more concrete. So we want to go back to the setting of volume constraints. So namely, we have for every edge some function that tells you for every time what's the maximum volume of flow allowed on this edge at that time. And we can now see how we can instantiate this constraint set and the set of admissible epsilon deviation. And for the set S, there's, I guess, a natural way, namely, it just contains all the path inflow vectors such that we never have a violation of this volume constraint. So the flow volume on any edge at any time is always upper bounded by the volume constraint. This is the set of feasible strategy profiles. And next, we have to define the set of admissible epsilon deviation. And there are now actually different ways we can do that. So one way is as follows. So we say we have some epsilon deviation, and we want to see if it's admissible. And to check that, we just compute the new flow after this deviation and check whether for the particles that are involved in this deviation, no volume constraints are ever violated by the time they arrive at their new edges. And if this is the case, then we say that's an admissible epsilon deviation. And this definition is actually inspired by something that has been done by Bernstein and Smith for the static case, which is why we call the resulting dynamic equilibrium the dynamic Bernstein-Smith equilibrium. So this gives us one type of dynamic equilibrium with volume constraints as side constraints. Another way is to take the idea of unsaturated alternatives more literally, basically by saying an alternative path in time is admissible for a deviation if at all times where new edges on this new path are reached, there must be actually some additional room on this edge, right? So we are truly unsaturated. And this, of course, also gives you an equilibrium concept. And we call this equilibrium concept dynamic Markov-Nguyen-Schwibb equilibrium, because again, those three authors considered a very similar model in the static case. And then, of course, I could go on, right? There are various other ways of defining admissible epsilon deviations, and they all lead to different kinds of equilibria. And now, so we have such equilibria. Next question, of course, is, do those equilibria exist, right? Is there such a flow satisfying these equilibrium constraints? And for this, a natural way of showing such existence is by just adapting the existence proof for unconstrained equilibria. And this is typically shown by characterizing these kinds of equilibria by means of variational inequalities, and then taking some existence theorem for solutions to these variational inequalities and showing existence of equilibria that way. And it turns out we can actually do this for these side-constrained dynamic equilibria as well, which leads to the following theorem. So if we have a constraint set S, which is convex, non-empty, closed, and bounded, and the set of admissible epsilon deviations, AP, also satisfies some niceness properties, then we are guaranteed existence of side-constrained dynamic equilibria. And the proof is exactly the way I just told you. We find a characterization of side-constrained dynamic equilibria by a certain variational inequality, which is very similar to the one for the unconstrained case. And then we show that the assumptions we made in the theorem are enough to guarantee existence of solutions to these variational inequalities. So, okay, we have existence. Now the question, of course, is within these types of equilibria we just defined, do they satisfy our assumptions? And there are some that are obvious, right? Non-emptiness, closedness, boundedness is usually not a problem. But the one that can be a problem, or is non-obvious, is convexity. So the question is, if we have, for example, volume constraints, is this set S convex? And for this, we can look back at our example we saw earlier, in this simple network, and let's assume we have some volume constraint on the last edge. And so this volume constraints and flow dynamics in this network is in such a way that if all the flow takes the upper path, like this, and there's some congestion on the first edge, and then flow enters the second edge, and it enters in such a way that the volume constraint of the second edge is never violated. And now we think the network is maybe symmetric. So the exact same would happen if we had all the flow entering the lower path. So we have two feasible flows in this setting, which of course means that if our set S were to be convex, then if we split the flow equally between the two paths, then this should again be a feasible flow like this. But we can already see a problem here. If we split the flow between the two paths, then there's less congestion, maybe even no congestion in this case. So flow arrives at the middle node V at a far higher rate. And so it enters the second edge at a higher rate. And this now leads to a violation of the volume constraint. In other words, in this setting here, we see that the set of feasible path inflow rates is non-convex. Right? So we cannot apply our existence theorem even in this very simple setting with volume constraints. So that's a bit sad, but we still wanted to show existence. And so we tried a different approach. And with some additional assumptions, but specifically not convexity, we were actually able to show existence of dynamic equilibria of the Marquardt-Nguyen ship type in the following way. So we make some assumptions, namely, first, the flow dynamics in the network have to have certain properties. And so specifically, we want that they are either modeled by deterministic queuing. So in the way I showed this in the animation, where the congestion is just modeled by queues on the edges, or via linear edge delays, where the travel time along an edge just depends linearly on the flow volume on this edge at the time particles enter the edge. The second assumption is that the side constraints are non-decreasing volume constraints, just like in our example. And thirdly, for every flow in this network, there must also be at least one unsaturated path. So there cannot be situations where some particles look at the network and they have no way of even entering it. There must also always be some open alternative for every particle. And if you have all these three assumptions satisfied, then we actually are guaranteed the existence of an M&S equilibrium. And to prove this, what we do is we relax our hard edge constraints and instead introduce a penalty function, which is proportional to the amount at which capacity constraint is violated. And then we add this penalty to our effective path delay operator, right? So the effective path delay is now just the sum of the original cost of the path plus the penalty. And the penalty is actually scaled by some parameter lambda here. And now with this new path delay operator, we can consider this as an unconstrained dynamic equilibrium problem. And by the known existence results for those, we get existence of unconstrained dynamic equilibria for each of those new path delay operators, so for every lambda. And now the interesting point is that if we increase this lambda, so making the penalty higher and higher, then the resulting dynamic equilibria we get for each of these lambda actually converge in a weak sense, but they do converge to a Marquardt-Nguyen ship equilibrium. And so this in particular shows, of course, existence of these types of equilibria. And so with this, I want to now conclude my talk by just briefly recapping what we have seen. We started off by defining an abstract general framework for defining side-constrained dynamic equilibria, which can be used for various types of side constraints. We saw the specific case of volume constraints, but you can, of course, think of many other types of side constraints that could all be implemented by this type of general framework. Then we saw existence of these types of side constraint dynamic equilibria, specifically for the case where the constraint set is convex and for the case of volume constraints. And in the process of that, we also were able to show characterization of side constraint equilibria under certain assumptions by variational inequalities and under certain weaker assumptions under quasi-variational inequalities. But of course, this is a new model, so there are still lots of questions open. In particular, I want to highlight two questions. One is more concrete, namely, the existence result we have presented here are quite abstract, right? They just use some abstract existence result, but we don't really know how these equilibria look like. We don't have really structural properties of those. And in particular, we don't have a real algorithm for computing them. It would be nice to get more combinatorial insight into these types of equilibria, which is something that has been done in the past for the unconstrained dynamic equilibria, specifically with deterministic queuing, which has been really helpful in understanding these types of equilibria. And the other question is maybe more informal, more abstract, but as you've seen, like this general framework allows the definition of a whole range of equilibria, and the choice of exactly what we use as a constraint set, in particular what we use as admissible epsilon deviation, leads to different types of equilibria. And so I think it's a very interesting discussion to be had, which equilibrium concept is actually the right one for a certain application. And we can certainly discuss this in the future.